Hello, everyone. A number of you have had trouble with homework set 21, and we're just kind of struggling with how to use the idea of curvature. And so I am going to go through the solutions to those problems, and hopefully that will be helpful. So let me share my screen here. Okay, so let's look at this first problem. Um, we have rays coming in parallel to the principal axis, and they are spread, they diverge from this negative lens. And then we're told that if we put this positive lens in just the right location, we can get those rays to leave parallel to the principal axis again. And so we're told that this is a beam spreader. We got parallel rays coming in, parallel rays coming out, but now they're spread over a wider area because this lens is spreading them out away from each other. Okay, and we want to find this distance d. Well, if we use our formula, k initial plus the power is equal to k final. Well, this is pretty easy because those parallel uh, those parallel rays have zero curvature. Okay, they're not curved at all. And then I add a -5 diopters, and that's going to give me K final. So I've got K final is equal to a -5 diopters. Now, what does that look like? Well, that looks like curvature that is spreading out, rays that are spreading from each other. Okay. And where does that curvature appear to be centered? Well, the radius is going to be 1 over the, oh, this is K, KF curvature. It's going to be 1 over the K. That's going to be 1 over -5. That's going to be -0.2. And that's meters. And that's going to be -20 centimeters. Okay. Okay, so if I go back to my picture here, maybe I'm need to see a bigger view. If I go back to my picture, that means that this all looks like it's coming from back here, 20 centimeters behind the mirror. Okay. Now, it doesn't stay -5 diopters. As it moves across, um, it evolves. And so it's going to be something different over here. And the question is, what is that something different got to be in order for this positive lens to give me zero curvature on the other side? So again, we use our formula. This time we're looking for the curvature right before that second lens. And so that's what we don't know. That's what we're solving for. But if we add +2 diopters, it gives us a total of 0. So that tells me my K initial right at the left side of that lens, it better be a -2 diopters. And that's a circle that appears to be coming from a radius of, let's see, 1 over K initial would be 1 over -2. diopters are meter inverse. And so that's going to be minus 50 centimeters. Okay. So that means that this thing uh, appears to have a radius of 50 centimeters behind it. Okay. Now, this is the same wave that was just evolving over to the other lens. So it also started or seemed to start 20 centimeters to the left. And so if this new radius is 50 centimeters, that means that the distance between them is 30 centimeters. So that's the final answer. They are 30 centimeters apart, okay? Because this had K of -2. This had K. This wave, when it leaves this lens, it had a curvature of -5, meaning that it was part of a circle that was centered 20 centimeters behind. When it gets over here, it has a curvature of -2. Again, that means that it's part of a circle that has a center 50 centimeters behind. And because these are part of the same circle, not the same circle, but the same center, um, this has to be 30 centimeters to make that 50 centimeters. Okay, let's go to the second one. In this problem, we start with a 3 centimeter object in front of a positive lens of focal length 40 centimeters. And then the light passes to another positive lens of focal length 10 centimeters. And you notice that the one with the smaller focal length I've drawn as a fatter lens. And that's because the the shorter the focal length, the more powerful the lens. Well, let's start by finding the power of these lenses. The power of this lens is going to be 1 over 40 centimeters or 0.4 meters. That's the focal length. And that's going to be a positive 2.5 diopters. The power of this lens is going to be a positive 1 over 10 centimeters or 0.1 meters. And that's going to be a positive 10 diopters. Okay. Now we have this, if we look at the light that leaves the tip of this arrow, and that arrow is representing, I believe, a pebble. Nope, nope. In this problem, by golly, it's an arrow. The arrow represents an arrow. Who would have figured? Okay. Well, when that light gets from that arrow to the first lens, because of this radius of 50 centimeters, it has a curvature of 1 over 50 or 1 over 0.5 or -2 diopters. Okay. By now you should be able to use that 1 over button on your calculator pretty quick there. So K initial is going to be -1 over 0.5 meters, and that's going to be -2 diopters. So if I do K initial plus power is equal to K final, what I get is I start with -2 diopters, and I add 2.5 diopters, and that's going to give me K final. So K final, I keep writing K with a F. I don't know why I do that. So K final is going to be positive 2, um, I'm sorry, 0.5 diopters. Now, a positive 0.5 diopters, well, that's not much curvature, but it's positive curvature. And that means it's going to be converging over here. Okay. And the question is, where does it converge? Where's the point where it's going to form a real image? And the answer there is that it is going to form a real image. Um, let's see. The radius of that circle is going to be 1 over 0.5 diopters, and that's going to be 2 meters. Okay, so if I go out 2 meters, let's see, where's 2 meters? That's going to be something out like this, okay? So it's going to come down here 2 meters. And that means it's going to be 20 centimeters from this second lens, okay? Now, this is going to be a real image because that's a positive lens. And that means it's going to be upside down. And I also know that it's going to be 4 times as big. It's going to be 12 centimeters tall. Scratch that. This thing started out 3 millimeters tall, and so this is going to be 12 millimeters tall. Okay, I have to stay true to the problem. Now, once that light comes together to form the real image, once it converges, the rays just pass right through each other and essentially propagate out, diverging as they go. And so by the time I get to this next lens, I'm going to have a K initial that's equal to 1 over 20 centimeters. Well, and it's going to be negative because it's diverging. And that's equal to negative 1 over 0.2 meters. And that's going to be a negative 5 diopters. So if I use my equation again, K initial plus power is equal to K final. This is a negative 5 diopters. I add 10 diopters, and that gives me my K final. So my K final, negative 5 plus 10 is going to be a plus 5 diopters. So that means it's going to be converging over here. And because this is 5 diopters, that's going to converge now a distance 20 centimeters from the second lens. Okay. Now, because, well, let's go back. Let's go back. We kind of skirted over something here. How did I know that this was 12 millimeters? Well, the answer comes from a, let me draw that more symmetric. If I send a ray through the point that is the symmetry of the lens, the very center of my lens, it does not get bent, okay? And that's because right there, the sides of the lens are pretty parallel to each other. And so what I have formed here is two similar triangles. And for similar triangles, triangles that have the same angles, the sides are proportional to each other. So if this distance is 50 centimeters, and this distance here is 4 times 50 centimeters, then all of the parts of this triangle are going to be 4 times bigger than all of the parts of this triangle. And so that means that if this is some height h, this is going to be 4h. And so since h was 3 millimeters, 4h is going to be 12 millimeters. Now, on the other hand, this real image is now the object in this second lens, causing a real image over here. And it is going to be 12 millimeters tall. And I know that because the distance on this side to the lens is 20 centimeters, and the side on this side is 20 centimeters. And so since the distances are the same, even though I haven't drawn it to scale, this is going to be the same size as that. Now, where is that final image going to show up relative to the initial point? Well, it's going to show up 20 centimeters to the right of the final lens. It's going to be 12 millimeters tall, and it's going to be upright. It's going to be a real image. This is the real image of this object, and this is the real image of that object. Okay, moving right along here. So here, we have a situation where we put a pebble. This one actually is a pebble that is 1 centimeter tall. And we want to know where the final image is. So let's just start. This is going to, let's look at light that comes from the tip of that, the top of the pebble, okay? And that's going to spread out. And the question is, where does it appear to be coming from? What's the curvature there? Well, no, I misspoke. It appears to be coming from right there. What's the curvature here? Okay. Well, the curvature, when it gets to that first lens, it's just going to be 1 over 40 centimeters or 0.4 meters. And it's negative because the light is spreading out and diverging. Okay. And that's going to be a negative 2.5 diopters. So if I use my formula, K initial plus power is equal to K final, I've got negative 2.5 diopters plus 5 diopters is equal to K final. That gives me K final is equal to a positive 2.5 diopters. Well, if negative 2.5 diopters comes from 40 centimeters behind, a positive 2.5 diopters is going to be curvature like this that looks like its center, the center of this circle is going to be 40 centimeters in front. And so that's going to give me a point right here, okay? Another 10 centimeters past the second lens. Now, the thing is, that image, that real image there, never gets formed. Um, if it had been formed, it would have been 1 centimeter tall. Okay, and we can again see that with a ray that goes right through the center of that first lens. Another way of seeing that is that it's 40 centimeters to the right of the lens. It started 40 centimeters to the left of the lens. The similar triangles say that these are going to be equal to each other. But like I said, the light doesn't actually get here because when it reaches this negative lens, the light is spread. Okay. And so this ray is going to head somewhere else. Well, let's find out where it heads. Okay. We need to find the curvature right here before it hits the second lens. Well, again, the center of the circle that this represents has its center 10 centimeters in front or to the right. And so that is going to be a curvature that is positive, and it's going to be 1 over 10 centimeters, which is 0.1 meters, and that's going to be a positive 10 diopters. So if I use my formula, K initial plus power is equal to K final, I've got positive 10 diopters, and then I add a negative 5 diopters, and that's going to give me a positive 5 diopters. Well, I know that a final curvature of positive 5 diopters, well, that has a radius of 1 over 5 diopters, or 0.2 meters, or 20 centimeters. Okay, so that is going to form an image here, 20 centimeters to the right of the second lens. And because it's twice as far away from this lens, it would be twice as big, 2 centimeters. And I can show that with a ray that goes through the center of this lens. Okay. So the light that was coming, the light that was coming through this lens, all wanted to gather here, but this ray here that would have gotten there got bent right here, and that ray went like that. Okay, so this one diverged the rays. So what we have here is a real image. How do I know it's real? Because the final curvature is positive, meaning these wavefronts are getting smaller and smaller, larger curvature, smaller radius, until they actually focus the light down here. I could put a piece of paper at this location, and it would project that image onto that screen. Okay. But in this problem, there really is only the one image, because this one never got formed because the light was diverted before we were able to form that image. Okay. Now, this one is similar to a problem that we worked in class in lecture. We have, we're told that this is 30 centimeters. And the focal length of this negative lens is 30 centimeters. And the focal length of this mirror, which is a converging mirror, is 15 centimeters. So let's start by finding the power. This is going to be a negative power, and it's going to be 1 over 0.3 meters, or negative 3.33 diopter. This is going to have a power that's positive because it's converging, and it's going to be 1 over 0.15 meters, and that's going to equal a positive 6.67 diopters. Okay. Now, we look at this curvature right before the rays that are diverging, right before they hit this first lens. The curvature is going to be negative. It's going to be 1 over 30 centimeters, or 0.3 meters. And that's going to be a negative 3.33 to infinity and beyond. Okay? Diopters. So if I do K initial plus power is equal to K final, I get negative 3.33 diopters, and then I add another negative 3.33 diopters, and that gives me K final. So I get K final is equal to negative 6.66 to infinity and beyond diopters. Now, what that means is that when it comes out over here, it's going to appear to be part of a circle that has radius of negative 1 over 6.66 diopters. And that's going to give me negative 15 centimeters. So it's going to appear to come from a point right there. 1, 2, 3. Yeah, okay. 15 centimeters. Okay. And it's going to spread out until it gets to this mirror. Now, when it gets to that mirror, it's going to appear to be part of a circle. You know I can't draw, but that circle is centered back here, 15 centimeters behind the first lens. And so since this is 105 centimeters and this is 15 centimeters, the radius of this appears to be 120 centimeters. So the K initial, when it reaches the mirror, is going to be a negative 1 over 1.2 meters. And that's going to give me 1.2, negative 0.833 diopters. Okay. So now if we do K initial plus power of the lens, of the mirror rather, is going to give me K final when it leaves the mirror. I've got negative 0.833 diopters, and then I add 6.67 diopters, and that's going to give me my K final of positive 5.83 diopters. Okay, now because that's positive, the light is going to uh, bounce back, uh, converging. Okay, well, where's it going to converge? Well, let's do the math. The radius of that circle is going to be 1 over 5.83 diopters, and that's going to be 0.17 meters or 17 centimeters. Okay. And so it's all going to come together right here. And it's going to form a real image. Okay. Now that's 17 centimeters to the left of the mirror. Now, when it spreads out again and gets to the lens, um, it has traveled a distance of 120, no, 105 centimeters minus 17 centimeters. Well, that's 88 centimeters. Okay. So when it gets back here, its curvature, let's go down here. Its curvature is going to be negative because it's spreading out, and it's 1 over 0.88 meters. Well, 0.88, 1 over, that's going to be negative 1.14 diopters. Well, what are we going to get when that goes through this lens again? Well, if I take negative 1.14 diopters and I add the power of that lens, which is negative 3.33 diopters, that's going to give me negative 2.2 diopters. No, that's not right. I forgot the minus sign. No, okay. 4 plus. That's going to give me negative 4.47 diopters. Okay, well, that's interesting. So when it comes out the other side, it's still going to be diverging. Well, it was diverging going in, and it's a diverging lens, so it's going to be even more diverging. And if I look for the center of that curvature, it's going to be equal to negative 1 over 4.47, and that's going to give me 22, negative 22 centimeters. The negative sign just means behind the wave. The wave is traveling now to the left through this lens, and the center of the circle it appears to be coming from is back here, 22 centimeters to the left of the negative lens. So that's the final answer, is that it ends up, the image ends up 22 centimeters to the, did I say to the left? I meant to the right, the other left. This is the lens, and the light appears to be coming from 22 centimeters uh, to the right of the lens, and the light appears to be coming from that point and spreading out. And so this would be an imaginary, not imaginary, but virtual image. So I have a virtual image. Now, what you see here is that when you have a mirror involved, these drawings get very messy very quick because the whole problem folds back on itself. And so I've got rays going this way to get to the mirror, and then rays going the other way to uh, get away from the mirror. And so maybe when you're dealing with a problem with uh, a mirror, you might want to bring a different color pen to the fight. And I should uh, follow my own advice. Okay. This fifth problem deals with the near point and far point of a child. And we're looking for uh, the different values of power for uh, the the lens in this child's eye. We know that she can focus everywhere in this region between her near point and her far point. Her near point being 8 centimeters in front of the lens of her eye, and the far point being 200 centimeters from the lens of her eye. So let's do the far point first. If I do K initial plus power is equal to K final. Well, the K final, you want to put an image right here. You want it to be a real image. If I put something here, I want the real image to form on her retina, which is 2 centimeters behind the lens. And so this is going to be a positive 1 over 0.02 meters. And I'm looking for the power. My K initial is going to be negative, and that's because light would be spreading out from the object there. And so that's going to be a negative 1 over 2 meters. And so if I solve for this, what I get is a negative half a diopter plus the power of the lens is equal to 50 diopter. So that means when she's looking at something at her far point, we'll call that power far, her lens has a power of 50.5 diopters. If I do that for the near point, well, it looks pretty similar. The power near, we'll call this far, the power near, my K initial plus my power near still has to focus it at 2 centimeters. So that's still going to be 50 diopters. Well, the K initial is going to be negative 1 over 0.08 meters plus P near is equal to 50 diopters. Well, this gives me a negative 12.5 diopters plus P near is equal to 50 diopters. Well, if I solve for P near, I'm going to get 62.5 diopters. So her lens, she has the ability to change the power of that lens from 50.5 diopters all the way up to 62.5 diopters. It's going to be the smallest value when she's focusing far away, as far as she can, and it's going to be the biggest value when she's focusing close to things. Now, we would like her to be able to see the mountains out here at infinity. And so the question is, what kind of lens should we put in front of her eye in order for her to see the mountains at infinity? Well, we know that she's nearsighted. She can see things close up, but not far away. And that means that um, we need a negative lens here, a diverging lens. But how strong should it be? Well, let's do this far point calculation again, but now um, we will do for P total, where P total is going to be the P of the glasses plus the P of her lens. Okay? And we know that that still has to focus on the back of her uh, eye. Okay? And so that still has to give me 50 diopters. Well, light coming from the mountains is coming in parallel with zero curvature. So K initial would be zero, and that means that P total needs to be 50 diopters. Well, the lens in our eye can't do 50. It can do 50.5, but it can't do 50. And so that means that the glasses have to have a power of negative 0.5 diopters. Okay? So the power of the lens of the glasses is negative 0.5 diopters. Now, what's that going to do to her near point? Well, let's do this uh, over again. Okay. Um, if I go to the near point, her uh, when she's got this uh, lens, the most powerful it can be is 62.5. If I add the glasses to it, that means the total power would be 62. Okay, so the power near plus the power of the glasses is going to be 62. It's 62.5 plus the negative 0.5 gives me 62. So if I do K initial plus the power of 62 diopters is equal to, it still has to focus on the back of her eye at the retina. So that's going to be 50 diopters. That means that K initial, oops, sorry, K initial, in order for this to be true, has to be negative 12 diopters. Well, how far away is that? Well, the radius of curvature there would be negative 1 over 12 meter inverse, and that's going to be negative 8.3 centimeters. So her near point is just going to move a little bit. It's going to move out just instead of 8 centimeters, it's going to move out to 8.3 centimeters would be the new near point. Okay, last problem. We have this bird that's 6 inches tall, and we have it 20 meters away. And if we use the tangent of theta is equal to the opposite over the adjacent, 6 inches over 240 inches. Well, 6 divided by 240, the tangent of that is a very, very small number of degrees. But, oh, the inverse tangent. 6 divided by 240 equals inverse tangent. That gives me 1.4 degrees. But we weren't asked for it in degrees. We were asked for it in radians. So let's switch our old calculator to radians and do that again. So 6 divided by 240 equals inverse tangent. And what we get is 0.025 radians. So 0.025 radians. Now, that's the answer to part A. Part B, let's say I'm making this number up. Let's say that you got binoculars that had a magnification of 30 times. That means that the new angle is going to be 30 times 0.025 radians. Okay. And so if I take that and multiply it by 30, I would get 0.75 radians. Okay. Now, for part C, I know that what that is going to look like is very different. Okay, we're going to have a new angle of 0.75 radians, where this was 0.025 radians. So the angle is going to be 30 times bigger. And what we want is how high would a bird have to be to give me this same angular separation between the head of the bird and the feet of the bird with my naked eye? Okay, how big would that bird have to be? Well, I would get that with the tangent function, and that's going to be my new height divided by the 240 inches. And so if I solve that for h, that's going to be 240 inches times the tangent of 0.75 radians. So if I take the tangent of that and multiply by 240, what I get is an h of 224 inches. Okay, and it's going to be a different number for you because you have a different magnification. And just to be clear, if you have something that magnifies 30 times, it's not binoculars that you're holding in your hand, because that's giving you so much magnification that the jiggling from your hands would drive you crazy. That's a spotting scope that you're going to need to mount on a very nice tripod. Okay. Well, I hope this has been helpful. If not, just stop watching it. Okay. I'm rooting for you guys. I think you can do it. I'm going to stop my share and I'm going to stop recording.